Okay, welcome, welcome back, guys. So we're still on trying to explain how Carl solved his teacher's challenge. There is also a simplified, I'll still explain this one. There's also a simplified way to solve using this, where for any given integer n is greater or equal to 1, you can just take out n plus n into n plus 1 divided by 2, which would give us the same answer. I will give the visual justification of proposition 3. Hello? Justification of proposition 3.3, which says this: A, the visual justify the proposition, both illustration visually, visualize the identity in terms of the total area covered by n unit width, rectangular with the height 1 to n. The lesson to be learned from the proposition 3.2 is that if we perform an algorithm with a nested loop such that the operation in the inner loop increased by 1 each time, then the total number of operation is quadratic in the number of times. And we perform the outer loop. To be fair, the number of operation is n squared divided by 2 plus n half. And so this is just over half the number of operation than an algorithm that uses n operation each time the inner loop is performed. The order of growth is still quadratic in n. And then we have the fifth function, which is the cubic function, and other polynomial. Or polynomial, the word comes from Greek, which says many forms. Continuing with our discussion of function that are powers of input, powers of input of the input, we have f of n, the engine, which is the function, which is n to the power of 3 or n cubic, which assigned to an input value n in the product of n with itself 3 times, which here we can have three nested loops, which have 3 for loops. The function appears less quickly. Is it me or what? I think there's some noise. Or maybe someone might try to switch off to mute the mic. This function appears less frequently in the context of algorithm analysis than the constants, linear and quadratic function previously mentioned, but it does appear from time to time. The polynomial, most of the functions we have listed so far can each be viewed as being part of the larger class of function called the polynomial. The polynomial function is the form of the f of s is equal to a sub 0, a sub, and this is a constant, the one that we talk about first, and it's a sub, and this is a linear, and then a sub 2 to the power of 2, this is a quadratic, and then this is a cubic, and sub 3 to the power of 3, and then polynomials. That's why it says in many forms. It says a lot of forms. We combine the all previously mentioned function, where a sub 0, a sub 1 to the a sub d are constants called the coefficients of the polynomial. And the a sub d is not equal to 0. Integer d, which indicates the highest power in the polynomial, is called the degree. These 2, 3, and d, and so on, are called the degree of the polynomial. For example, the following functions are all polynomials. F of n is equal to 2 plus 5, n plus n squared. This is a polynomial of 2, which is highest degree is 2. Therefore, this is a quadratic function, this is a cubic function, this is a constant, this is a linear function, this is a quadratic function. We could argue that this book represents just the important function used in algorithm analysis, but we stick to the saying that there are 7, since the constant, linear, and quadratic function are too important to lump in with other polynomials. That's why quadratic, linear, and constant are made important, highlighted more because they are too important to the algorithms. In mathematics, there's something called summation with capital Greek S alphabet, a notation that appears again and again in analysis of data structure. An algorithm is called a summation, which is defined as follows: the sum of I is equal to 1 to P is equal to f of I plus f of I is equal to f of A plus f of A plus 1, f of A plus 2 until the last mention, which is P. Which we, in our previous example, we can call this is 100, the end of summation that we need to add. Where A and B are integer and A is less than or equal to B, summation arising in data structure and algorithm analysis because of the running time of loops naturally give rise to summation. The same loop we did, which is say, okay, 100, and then summation I is equal to 1, and then you say n 100 into 100 plus 1 all divided by. So this is a simplification of what Gal in the 17th century did. So you say 100 into 100. So this would give us 100 into 101 over 2. 100 times 100, you can do it mentally. If you want to do it mentally, you can just say 100 minus 1. I mean 101 minus 1, which just give us 100. And then times 100, this 100, outside 100. So 100 times 100 is we just put 1, and then you add these zeros, which is 10,000. And then we must add 100, which will be 10,000 and 100. And then remember this 2 that we divide it, divided by 2, that will give us 5,050. This is what summation does. So n into n plus 1 over 100. Likewise, we can write a polynomial f of n of a degree d with a coefficient a sub 0 to a sub d is f of n is equal to d, equal to summation, equal to I is equal to 0 summation of d a sub I times n to the power of I. As the summation notation gives us a shorthand or a short way to express the sum of the increasing terms that have a regular structure. And then we have the sixth, which is exponential function. Another function that is used in analysis of algorithm is exponential function. The f of n, the engine, is equal to the f of n, the engine, f of n engine, which is equal to, this is, remember, this is our engine, equal to b to the power of n exponential, where p is a positive constant called the base, p is our base, and then the argument n is exponent. That's the one that will raise the power. That is function f of n assigned to the input argument n, the value obtained by the multiplying the base by this b by itself to n times. As we are the case with the logarithm function, the most common base for the exponential function is algorithm analysis is b is 2, because computers run on the binary number. For example, the integer weight containing n bits can represent all the integers less than 2 to the power of n. We have a loop that starts by performing one operation and double the number of operations performed with each iteration. Then the number of operations performed in nth iteration is n to the power of is 2 to the power of n. Sometimes we have other exponents beside n. However, hence it is useful for us to know a few handy the rules for working with exponent, in particular the exponent rules. The exponent rules are given a positive integer a, b, and c. We have b to the power of a, all these brackets, all in c. So we can as well say as b to the power of a times b. If it's b to the power of a times b to the power of c, you can just say b is the same as b to the power of a plus c. If b to the power of a divided by b to the power of c, you can say b to the power of a minus c. E.g., 256 is equal to 16 squared, or 16 to the power of 2, which is 2 to the power of 4 times 2, which is, we can also say the same as 2 to the power of 4 times 2, which is same as 2 to the power of 8. Same as give us 256 exponent rule 1, this rule. You can continue to the exponent rule 2, etc., etc. You can extend the exponential function to the exponent that are fraction or real numbers and to negative exponents as follows. Given a positive integer k, we define b to the power of 1 over k to be the k roots of p. That's the number r, such as r to the power of k is equal to p. E.g., 25 to the power of half is equal to 5. 25 to the power of 2 is equal to 25. Likewise, 27 to the power of 1/3 is equal to 3. 25, 16 to the power of 1/4 is equal to 2. This approach allows us to define any power whose exponent can be expressed as a fraction. We can further extend the exponential function to define b to the power of x for any real numbers x by computing a series of numbers of the form b to the power of a over c for a fraction of a over c that gets progressively closer and closer to x. Geometric sum. Suppose we have a loop for each iteration takes the multiplication factors longer than the previous one. This loop can be analyzed using the following proposition. For any given integer n is greater or equal to 0, for any real number a such that a is greater than 0 and a is not equal to 1, consider the summation. We can work on a summation, but a geometric sum, it means it's either goes exponential, like we say 1 plus a is 1. The second addition is a to the power of n. The third one, a to the power of 3, until a to the power of n. Certain number that we have here. Remember that a to the power of 0 is equal to 1. If a is greater than 1, the summation is equal to a to the power of n plus 1 minus 1 over a minus 1. Summation is shown in proposition 3.5 called the geometric summation. It progresses or grows exponentially. The growth, comparing the growth rate, to sum up the table 3.1 shows in order that each of the 7 common functions used in algorithm analysis. We have the first one, which is constant, which has a number. Then the second one is corrective log of n base 2, and the third one which is linear, and the fourth one which is n times log of n base 2. The fifth one which is n squared quadratic, and then the sixth one is cubic, n to the power of 3, and then the last one which is exponential, n to the power of n. Ideally, we would like the data structure operation to run in this time proportionally. to the concept of recursive function, we would like our algorithm to run in a linear or log n of times. The algorithm with quadratic or cubic running times are less practical, and algorithm with exponential running times are infeasible. The plot of the 7 features that are shown, you can see, okay, this is exponential exactly, which is here, is go straight up, short up. And then we have the one that grows linear up, which is the cubic. And then we have a quadratic, which is goes up. And then we have log n times n, which is just a little bit above of the linear. And then we have a linear, and then we have a logarithm, which is here down. And then we have a constant, which is goes straight on the same line. The growth rates for the 7 fundamental functions used in algorithm analysis we use. Base A is equal to 2 for exponential function. The function plotted on a log chart. To compare the growth primarily as slope, even so the exponential growth grows too fast to display all values in the chart. And then we have what we call the ceiling and floor function. The floor function is the largest integer less than or equal to x. And the ceiling is the smallest integer greater than or equal to x. The asymptotic analysis is how our algorithm goes. Where asymptotic analysis it's an algorithm that refers to defining the mathematical foundation or framework, how the framework of its runtime performs. Or the performance of our algorithms, we use what you call asymptotic analysis. So when we're comparing our function that we those 7 function that we're talking about. Using asymptotic analysis, we can very well conclude that there is a best case, average case, and the worst case. In this book, we mostly use the worst case, where asymptotic analysis is input bound. In essence, if there is no input to the algorithm, it is concluded to work in a constant time rather than the input on all the function. In algorithm analysis, we focus on the growth rate of the running time as a function of the input. As taking a bigger picture approach, for example, it is often enough just to know that the running time of the algorithm grows proportional to n. So it's controlled by n, so it must always go proportional to n. We analyze the algorithm using the mathematical notation for function that disregard the constant factors. Namely, we characterize the running time of the algorithm by using the version that are map the size of the input and to evaluate the corresponding to the size, the main factor that determine the growth rate in terms of n. The approach we reflect that each basic step in a pseudocode described or higher level language subsection or a higher language level. Implementation may correspond to a small number of primitive or operation as we can perform an analysis of an algorithm by estimating the number of primitive operation executed up to a constant factor, rather than getting a bogged down in a language specific or hardware specific analysis for exact number of operations that execute on the computer. As a tangible example, we revisit the goal of finding the largest element of a Python list. We first use the example when introduced loop on, and this was we did in private. So if you wanna just say define the maximum, it is the function of find the max of the data. The biggest is of the first in the list one is the biggest for while in the data. The loop goes here. So if the while if the first one it goes, okay, if the val is greater than the biggest, is greater than the first one, the biggest is equal to the val, and then return the biggest. Let's see if we can try to run this one. What is it? Where's the list? So this is where we said we're gonna run our group. So we said def and max data. If val is greater than biggest. And then we say the biggest given to val. Okay, let's create the data. One, four, three, seven, 7. You can see yeah the biggest number here is 9. So this, if it's good, it should, if it's done well, it should give us, it should give us the highest number. So need to print. Then after we run this, and then we need to print the time. How long do you have? We need to print the runtime. Of gonna run. Some errors. branch from this. Yeah, it is at the end, but it's run fast. If it's already in ordered number, it's run fast. So we're gonna try to run this random number, which is it take more time than, and then if we run, and then we're gonna try also to run a sorted one, it's just a straight. I think there's an error here. Minutes. I think it doesn't make clear because now it's not clear. You can see the number, the highest number in the list is in the list is 9. You can see our biggest number here is 9, and then the runtime is 0.000 blah, blah, blah. So we have a runtime of, let's say, 1%. One of the fastest time because it's running on a, because it's running, it is a linear equation. It is a linear function. Calculate this one. Okay, let's see if do we need to put it runs from because it's sorted now, it's go straight. It doesn't have to look to all. It runs from 005 compared to this one from 0015. So the running time differ from the sorted one compared to the just the normal one. Okay, we're gonna start to the peak. Oh, that would be interesting because it's gonna. Okay, maybe we can just read because only 7 minutes or 8 minutes. Okay, this is a classic of an algorithm with a running time that goes proportional to n as the loop. As the loop executes once for its element with a fixed number of primitive operation, executing to each pass. In the remainder of this section, we provide a framework to formulate this claim. Okay, we saw that we ran this function or method, and then which was on a linear function because it only ran only on the list, only ran once, then ran on the list. Then second one, and on a 3.3.1, we have a big O notation. The big O notation, it is a framework of mathematical work that combine f of n and f of g by functioning mapping positive integer to positive real numbers. We say that f of n is a big O of g of n if there is any real constant c is greater than 0 and an integer constant n initial n or n sub 0 is greater or equal to 1, such that the f of n is less than or is equal to c times G of n for n is greater than the first number. This definition is often referred to as the big O notation for sometimes pronounced as f of n is big O of G of n. Big O deals with the worst case scenario. We call a big O is asymptotic upper bound. Remember, we said asymptotic is where we calculate how fast we analyze our line, our analysis, our function. So the notation big O for n or big O of n is defined as the formal way to express the upper bound of n of an algorithm running time. It is the most common used notation. It is measures the worst case time scenario or complexity, or the longest amount of time an algorithm can possibly take to complete. The function of n can be represented is the order of G of n, that is the peak of G of n, if there exists a value of positive integer n, n sub 0 and positive constant c is such that, as I'm saying. So you see here where they compare the function c of G of n with the function f of n. The illustration of the big O notation, the function f of n is the big O G of n, since the f of n is less than or equal to c times G of n when n is greater than or equal to n of n. This is n of 0. If f of g is less than or equal to c of g, so the f of n is less than, because you see this line goes under the, and is lower than the c of g of n, cg of n. The function hn plus 5 is the peak of n. To justify that the peak of definition, we need to finally get the real constant c is greater than 0 and an integer constant n of 0 is greater than or equal to 1, such that 8n plus 5 is less than or equal to cn for every integer n is greater than or equal to n0. It is easy to see that a possible choice is c is equal to n is equal to 9 and n of 0 is equal to 5. This is one of infinitely many choices available, because there is a trade-off between c and the input n of 0. For example, we can rely on a constant c is equal to 13, and then the input n of 0 is equal to 1. Big O notation allows us to say that a function f of n is less than or equal to another function of g of n up to a constant factor in an asymptotic sense as n grows to infinity. This ability comes from the fact that definition uses less than or equal to compare the f of n to h of n times a constant. Remember, we said big O calculate or analyze in a worst case scenario. So that's why it uses less than or equal to. Since the big O already denotes less than or equal to concept, likewise, although common, it is not fully correct to say f of n is equal to big O of g of n, with the usual understanding of the equal sign relation, because there is no make sense of the symmetric statement. Big O of g of n is equal to f of n. It's better to say the big f of n is the big O of g of n. Alternatively, you can say f of n is the order of g of n. For more mathematically inclined, it is also correct to say f of n is the element of big O of g of n. For the big O notation, technically speaking, it's the whole collection of functions. In this book, we stick to the presenting the big O as element as f of n is a big O of g of n. Even with this interpretation, there's still a considerable freedom in how we can use arithmetic operation with big O notation. With this freedom comes a certain amount of responsibility, as Spider-Man will say. The characterizing running time using the big O notation. The big O notation is used widely to characterize the running time and space bound in terms of some of parameter n, which varies from the problem to problem, but is always defined as a chosen measure of the size of the problem. For example, if we are interested in defining the largest element in a sequence, as we did with the find maximum algorithm, we should let n denote the number of elements in that collection using the big O notation, and we can write the following mathematical characterizing statement on the running time of the algorithm find, the one that we did before, to any computer. The algorithm find mass computing the maximum element of the list of n number run to the linear big O of n time. So it's a linear function. I think because we're less than a few seconds, we're gonna end here. Maybe during the week, and then we can start to continue with others. If there's anything, because I don't even think we can have a question.